Although Recon-All usually does a good job of reconstructing the cortical surface, sometimes it fails. These failures can be classified as either hard failures or soft failures. A hard failure is when Recon-All exits prematurely, when it doesn't have write permissions, or when there is no more available disk space. A hard failure can also occur if you have excessive motion or other artifacts in your T1 image. If you check the file reconall.log in the scripts directory, and the last line says that Recon-All exited with errors, you can assume it's due to one of these causes. Hard failures are uncommon and easy to fix. More common are soft failures, when Recon-All completes successfully, but there are still errors in the surface reconstruction. The result is either 1. Inaccurate segmentation of the white matter, or 2. Inaccurate peel surface reconstruction. Fixing this requires editing the volume, because it is not possible to edit the surfaces directly. There are 5 types of soft failures: skull stripping errors, peel surface errors, intensity normalization errors, topological defects, and white matter segmentation errors. A few words about these last 2 cases. Topological errors, that is, holes punched through the white matter, and thin handles connecting distant gyri, are usually fixed automatically by FreeSurfer. White matter segmentation errors are usually restricted to branes with lesions. To learn more about fixing these errors, I recommend working through the examples provided in this link. Now, let's return to soft failures. To detect these errors, you will need to become fluent with looking at both volumes and surfaces in FreeView. The main volumes you will look at are the T1 and brain mask images in the MRI folder, and the main surfaces you will look at are the peel and white matter surfaces. From your subject's dir directory, you can type the following to load all of these. Take a few minutes to scroll through all the slices in all of the views, noting whether the outline of the peel surface and the white matter boundaries seem reasonable. If the boundary looks out of place, you will need to edit the volume. However, keep these caveats in mind. If something looks like a misplaced surface boundary, but it is only apparent for one slice, my recommendation is to leave it alone. Also, the surface boundaries along the medial wall around the corpus callosum and subcortical structures are not used in the final surface calculations, so they can be ignored. If you do need to make an edit, you have 4 options for editing. You can erase voxels, fill in voxels, add control points, or clone voxels from another image. We'll cover these in more detail when reviewing how to fix each type of error. Before we start, keep 3 things in mind. 1. Make a backup folder of the subject you are editing. If you make a mistake, it can be difficult to undo it. Edits that are saved are permanent, just like your insecurities. 2. Remember that editing the data too much can make the surfaces worse. Be conservative when editing. If your data quality is good, Recon-All will be very accurate in creating the cortical surfaces. If you find yourself having to make many edits per subject, this is most likely a problem with your data quality, and it should be fixed at the scanner, not in FreeSurfer. Lastly, if you're unsure of whether to make an edit, don't do it. Remember that we're editing 3-dimensional volumes, and what looks like a problem in one slice may resolve in the next slice. Removing the skull, or skull stripping, is an early step in Recon-All. This ensures that FreeSurfer does not misidentify the skull or the dura mater as cortex. However, sometimes the skull stripping is too aggressive and begins to remove cortex, or not enough skull is removed. These extreme cases can usually be fixed by changing the watershed threshold in Recon-All, which identifies the boundary between the skull and the cortex. Lower values for the WS Thresh option in Recon All will remove more skull, while higher values remove less skull. However, when the skull has been mostly removed but excessive dura remains, a better option is to use the G-cut option. Here we see that the peel surface latches onto the dura for several slices. First, make a backup copy of your subject directory. Then type the following command. It should take about a minute. You can overlay the resulting file, brainmask.gcuts.mgz, on the T1 image and the peel surface to see where the dura was removed. If you believe this fixed your problem, then run the following command. This runs all of the steps after skull stripping with the newly stripped brain. In this case, however, we can see that although some dura was removed, it wasn't in the areas that were affecting the peel surface estimation. You could try more aggressive skull stripping parameters, but this may cause more problems than it solves. In this case, I recommend a peel surface edit, in which we manually remove voxels. First, make sure that brain mask is highlighted, so that our edits will only apply to that image. Then click this button, which enables voxel editing. Holding Shift and left-clicking removes voxels, and you can undo the last edit by pressing Command and Z. First, note the slice where the problem begins and where it ends. In this case, I've chosen slices 92 to 106 to bookend my edits. Erase those voxels which seem to be part of the dura. Again, be conservative and take care not to erase cortex. Once you're done, click on File, Save Volume. Then you can run Recon All starting at the peel reconstruction stage. Once this finishes, check the peel surfaces before and after to make sure it did a good job. Another common class of errors are intensity normalization errors. Usually in this case, white matter is incorrectly labeled as gray matter. This happens most frequently in the ventral temporal lobes and the orbital frontal areas. To fix this, we will use control points, which boost the intensity of the voxels surrounding the control point. You can find these errors in any viewing orientation, but I find it easiest to detect OFC and ventral temporal errors with the axial view. As in the last video, note the slices where your error begins and where it ends. Here, I'm focusing on slices 152 to 156. To add control points, click on File, New Point Set. Call it control.dat, and make sure the brain mask image is selected as the template. Add control points by left-clicking voxels that you think are white matter but aren't included in the white matter boundary. Space out each control point by at least a couple of millimeters, and do them for each slice that contains the error. When you're done, click on File, Save Point Set As, and call it control.dat. Save it in the temp folder. Then run this command. When it finishes, compare the white matter segmentation before and after. That concludes our overview of common FreeSurfer troubleshooting modes. Before we leave each other, keep the following points in mind. First, once you get a feel for how to detect and fix certain errors, plan on spending about 10 to 20 minutes per subject. The point is to detect and fix the major errors. If you spend too much time troubleshooting, you become more likely to make a mistake trying to fix something that may not be an error. 2. I find that skull stripping errors are more easily detected using the sagittal and coronal views, whereas intensity normalization can be seen in any view. And lastly, remember that we're looking at 3D structures with 2D viewing panes. Something that looks like an error in one window may resolve later on, or it may make more sense when you look at it from all 3 views. And with that, we've finished the basics of FreeSurfer and troubleshooting modes. I hope this helps, and I'll see you all next time.